presentation, which we will play now. So this is about, the paper title is Side-lobe can know more, so towards simultaneous communication and sending for millimeter wave radars. And we can play the video, please.
Qianyi from Southern University of Science and Technology. Today I will present our research team's work, a simultaneous millimeter wave communication and sensing system using side-lobe sensing. With the evolution of wireless applications, we have witnessed the emergence of transformative technologies like the vehicle-to-everything, digital twins, and virtual reality. These applications all share a fundamental need: high throughput and low latency in data transmission. Compared to the current sub-6 GHz communication spectrum, we highlight the millimeter wave band, where a huge bandwidth resource is available. The communication standard in mmWave band is support up to 2 GHz bandwidth and 7 gigabits per second data rate. At the same time, previous work has shown that mmWave also has superior performance for sensing. Thus, exploring the joint design of sensing and communication in the mmWave band is a hot trend, leveraging its full potential to the utmost extent. mmWave communication devices are usually mounted with a phased array antenna to compensate for propagation loss, and use beamforming to concentrate the radiation or reception range into a narrow sector. Existing mmWave communication systems improve the sensing range by beam training. However, this brings the dilemma between sensing and communication in the mmWave band. When the AP is performing beam training, it can sense the environment but no data communication. When AP and stations are communicating, the directional beam constrains the sensing range. Different from the above time multiplexing strategy, multi-beam solutions are proposed, where there is a fixed directional beam for downlink communication and the other sweeping beam for sensing. However, the sensing beam may interfere with other devices. Moreover, since the transmission power is shared between the communication and sensing beams, the communication link signal-noise ratio would decline. We observe that in directional transmission, where most of the power is concentrated towards the communication direction, the remaining power is distributed over all angles, for example, side lobes. We propose Sidense, which can use the transmitter side lobe for sensing and the main beam for communication. Side lobe-based sensing can operate simultaneously with communication, and there are no modification requirements for current standards, without degrading the communication performance. In Sidense, the mmWave access points transmitter and receiver are co-located. The transmitter performs downlink data communication with associated clients, while in the meantime, the receiver monitors ongoing activities in the surroundings. We put forward 3 design goals. Sensing needed to cover the general indoor range, support multiple users, and support long-term continuous sensing. To achieve these goals, the first challenge is that the energy of the side lobe is always much lower than the main lobe. We found that about half of the side lobe direction gain is 16 dB lower than the main lobe, which will reduce the sensing distance by about 60%. Inspired by coherent integration in radar signal processing, N-packet accumulation can theoretically improve the SNR by N times. Due to the large bandwidth in mmWave communication, there are numerous packets in a short interval, for example, 1 millisecond. Thus, we boost the channel impulse response by integrating successive packets per impulse. Due to the long uniform transmitter side lobe gains, targets located in different sectors require different integration gains to achieve the same signal-noise ratio. When dealing with multiple targets at different angles, Sidense organize them based on TX gain, starting with the highest gain, which needs the fewest accumulation packets. For the next target angle, AP will update the integration time. This process continues until all target sectors are scanned. With such a design, targets with a larger gain gap can achieve a longer integration interval effectively improving the sensing range. The second challenge is the mutual interference in a multi-target scenario. Since the phased array antenna has a single channel output, reflections from all targets are superimposed on the RX side. This makes it hard to decouple the mutual interference between multiple targets. To decouple mutual interference, according to received signal linear superposition model, it can be divided into static and dynamic components depending on the motion of the target on the propagation path. The static component can be calculated and removed by the received signal expectation within a certain duration. As for the decomposition of dynamic components, the first step is to select high-quality observations for separation. We use target movement frequency as indicators. According to the frequency indicator, we categorize the selected periodic signals into distinct observation groups, and then perform independent component analysis on each observation group. Finally, we get a set of separated components. To separate the interference from the text main lobe direction, we adopt the windowing to reshape the RX beam, a straightforward but effective way to separate the interference. The third challenge is that when the location of the client changes, the AP will switch the transmitter beam to realign the client. This will change the distribution of signal energy on each propagation path. The target motion sensing can be interrupted by text beam switching. We recover the interrupted signal by implementing background removal on the received signals in different combinations of transmitter and receiver beam directions. We implement Sidense with Sivers 6 GHz mmWave module and software-defined radio. Results show that Sidense can achieve robust sensing performance under different indoor environments. Communication performance is barely impacted when systems engage in simultaneous sensing. Sidense also can provide more interference separation in the text main lobe direction. We also showcase the capability of Sidense with a multi-person respiration monitoring application. In conclusion, we designed Sidense, a mmWave transceiver that simultaneously performs directional downlink communication and omnidirectional sensing. Here, I'd like to briefly talk about the limitation and future research. One of the limitations of Sidense is the target motion resolution will be limited by adaptive coherent integration. In the future research, we consider use beam optimization techniques to further suppress motion interference. We also can use Sidense system model to accelerate in mmWave link communication. Thanks for your attention. Any questions?
Yeah, for questions, please reach out to the author via email. And so the next